Hello everyone, welcome to the channel Statistical. So in previous lecture we are doing elementary operations. Okay, and these elementary operations are used to reduce a matrix. Okay, now we'll see that what are the reduced forms of the matrices. Okay, what are these reduced forms of the matrices? Okay, so we will study here three types of reduced forms, that are echelon form, canonical form, or you can say row reduced echelon form. Row reduced echelon form, and the other one is a normal form. Okay, so we will see these three types of reduced forms of the matrices. Okay, so we have done echelon form in the previous lecture, and we have seen there that a matrix is said to be in its echelon form if it satisfies these properties, which are like, the first one is that all zeros, if any, exist in the matrices, then if all the zero rows are at the bottom of the matrix, at the bottom of the matrix. Okay, and the second property that it should satisfy is that each first non-zero element in a row is on right hand side of first non-zero element in preceding row, or we also say that all entries in a column below a leading entry, below a leading entry, or you can say pivot column, pivot entry, pivot element, uh, leading entry or pivot element are zeros. Okay, so our echelon form, if you take an example of echelon form, then our echelon form looks like this. 4 0 0 0 0. Okay, so this is our echelon form, how it looks like, and these are the pivot elements. Okay, these are the pivot elements. So if you look into the definitions of the echelon form, that all zero, if there exists a zero row. Okay, so let's just consider 3 cross 3 matrices, and the echelon form of this 3 cross 3 matrix is like, okay, so if there exists any zero row, that should be at the bottom of the matrix, at the bottom of the matrix, and all entries in a column below a leading entry, this is my leading entry, and below these leading entry we have all the entries as zeros. Okay, we have all these entries as zeros here. So these are how the echelon forms are. Okay, so sorry, this is not in leading entry, this is the leading entry. So below this is it says is its element is zero. Okay, so this is how we represent an echelon form, echelon form. Okay, and this is what, this is pivot. Okay, now we will see row canonical form or row reduced echelon form. Row canonical form or row reduced echelon form. Okay, so what are these? So these canonical form is basically obtained by echelon form of the matrix. Okay, so an echelon matrix with with these properties like each pivot, each pivot is equal to 1, is equal to 1. Okay, we are saying that each pivot element has to be equal to 1, and second one is that each pivot is the only non-zero entry in its column. Okay, So after reducing a matrix into echelon form, echelon matrix, we have to satisfy these two conditions, which are like each pivot is equal to 1 if I have each pivot element which is 1, and each pivot is the only non-zero entry in its column. So if we look into the echelon row canonical form, then the row canonical matrix, row reduced echelon form matrix looks like something like this. You can take the identity matrix. So identity matrix basically satisfies these conditions. You can see it that I have these as my pivot elements. These are my pivot elements, and all these pivot elements are one. Okay, and each pivot is the only non-zero entry in its column. Okay, this is the column. This is the only non-zero entry here, and similarly here we have this, and this is the only non-zero entry here. Okay, now the echelon row canonical form can also look like this: 1 0 0, 0 1 0, and 0 0 0. Okay, and these are the leading entry here. Okay, and in this it can be a number. Okay, because it doesn't contain any leading entry, any leading uh, entry in this column, so this can be a number. Okay, so this is also a canonical form. Okay, basically we have to satisfy these two conditions for a matrix to be said in its row canonical form. Okay, now if we talk about any n cross n non-singular matrix. Okay, so this is a n order matrix which is non-singular. Okay, so as this matrix is non-singular, now this matrix can be reduced to identity by elementary row operation. Okay, how? Why I'm saying that? I'm saying that if this matrix is non-singular, that means its uh, rank of this matrix, rank of this A has to be equals to n. Okay, as its rank is equals to n, then we have this matrix. We have this matrix after applying elementary operation. We can reduce this matrix to a matrix into identity format, which is of n cross n. Okay, so by this we say that any non-singular matrix can be reduced to identity by elementary row operation. We are talking about the non-singular matrices. We didn't say anything about the singular matrices, because in singular matrices rank can be less than equals to n, but in non-singular matrices we have rank of A as equals to n. Okay. Okay. Now you have studied about the equivalent matrices. Okay, equivalent matrices. Equivalent matrices. So we when can we say that two matrices are equivalent? We denote the equivalent sign like this. Then two matrices, let's say we have two matrices A and B. These are two matrices which are of same order. Same order. These matrices are said to be equivalent if one can be obtained by one can be obtained from other by finite chain of by finite chain of E transformation. E transformation. Okay, so this is the condition for the equivalent matrices. Okay, now there are three properties of relation for the equivalence relation, that are reflexivity. Okay, we have done this so many times, that the equality conditions are it should be reflexive, that is A should be equivalence to A. Second is symmetricity, that is A is equivalent to B, that means B is equivalent to A. Similarly, third property is transitivity. Transitivity, that means A is equivalent to B and B is equivalent to C, then it implies that A is equivalent to C. Okay, so this is the condition when we say that the two matrices of same order are equivalent if one can be obtained from other, if we apply a finite chain of elementary transformation on that matrix. Okay, now the important note here is that every matrix Every matrix A is row equivalent to a unique matrix in row canonical form. Okay, so every matrix A is what is a row equivalent to a unique matrix in row canonical form. Okay, now if we look into the rank part here, okay, we are doing the rank concept in the earlier lectures also. So in the rank concept, we can say that in the echelon form matrices, that number of non-zero rows in the echelon form of a matrix is its rank. Okay, what into the, if we look rank, then number of non-zero rows in its echelon form are rank. Okay, and similarly, if we have two matrices which are equivalent, as A is equivalent to B, then rank of A, it means rank of A is equals to rank of B. Okay, and there is one point to note here is that the elementary transformation of a matrix do not alter its rank. Okay, that is, elementary transformation of a matrix do not alter its rank. Okay, the elementary transformation does not cause any effect to the rank of a matrix. Okay, so two matrices A and B, which are we are taking here two matrices A and B which are of same order, and these matrices are said to be equivalent if they have same rank. Okay, and the rank of a matrix, there is another point to note here is that the rank of a matrix does not change on pre or post multiplication with a non-singular matrix. Okay, we have done this in the in the rank concept, that a rank of a matrix does not change on the when we on pre and post multiplication with a non-singular matrix. Okay, now let's just so this is the rank concept here with respect to the echelon form. We can easily find the rank by reducing a matrix to its echelon form, and the number of non-zero rows in its echelon form are rank. Okay, now let's just see the normal form of a matrix. Normal form of a matrix. Okay, so in its normal form, a matrix is said to be in its normal form if it is represented like IR 0, 0, 0. Okay, for some R. For some R, if a matrix after the transformations can be represented like this, then this is said to be in its normal form. Okay, so if we take, let's say if R is equals to 0, that means then it is null matrix because it will be 0. The all I R is it will I 0 will be 0. So this is, it is a null matrix. Okay, now there is an important theorem in this normal form of the matrices that says like this, that if we have a matrix A of m cross n which has a rank R, okay, that means rank of A is equals to R. Okay, then if the rank of the matrix is R, then there exists a non-singular matrix P, matrices P of order M and Q of order N, such that PAQ is equals to IR 0, 0, 0. Okay, where P is what? P is my elementary matrices corresponding to row, and Q is elementary matrices corresponding to column. Okay, these are what elementary matrices corresponding to row, and this is also elementary matrices corresponding to column. Okay, so if we have a matrix which is of order m cross n, and the rank of this matrix is R, okay, then there exists a non-zero matrices which is P, that is elementary matrices corresponding to row, and of which is of order m, which is of order m. Okay, because we are talking about the row and there are m rows here. Okay, and Q is elementary matrices corresponding to column, which is of order n, as there are n columns in the matrix. Okay, such that PAQ is equals to IR000. These are what? These are the transformations applied on this matrix A for reducing it to this form. Okay. So if we take R is equals to P inverse, okay, and S is equals to Q inverse, okay, then we can rewrite this equation 1 as, we can rewrite it as like A is equals to R IR 000S, where these are the corresponding. R is equals to P inverse and S is equals to Q inverse. Okay, so this is the normal form of the matrices. This is the normal form of the matrix. Okay, now if you look into the rank factorization of A, okay, the rank factorization of the matrix A here. The rank factorization of A, then what is our R? R is actually R1, R2. Okay, and S is, because S of it, S is corresponding to the columns, so it is S1, S2. Okay, and according to the rank factorization, we have R1 of M cross R and S1 of R cross N. Okay, so the rank factorization of A, this gives us is actually R1 S1. Okay, because A is equals to R1 S1. So we have R1 S1 as these are of order M cross R and this is of order R cross N, and we have A of M cross N, and that this is R1 M cross R and S1 R cross N. So by multiplying these, we got our corresponding matrix A, which is of order M cross N. So from this, as R is the P inverse, R is the P inverse. So if we take R1, which is of order M cross R, okay, and from S we take S1, which is of order R cross N, then we will get our rank factorization of A, which is R1 S1, and the R1 S1 matrices is rank factorization of matrix A. Okay, so this is how we can find the rank factorization um, for the matrix by the normal form. Okay, now we have been using elementary transformation in computing inverse too. Okay, so what are we doing? Use of E transformation for inverse. So in the inverse topic, we are applying it like this, that we have A is equals to IA. Okay, I have done this earlier too, that if we have to find the inverse, we'll write this in matrix A into this format, that A is equals to IA. Then we'll perform transformation and we'll make it identity equals to B into A. That is, we have to perform the transformations on, and we have to make A to identity, and we'll apply same transformation to this identity, so it will be transformed to matrix B. Okay, now on post multiplying A inverse in this, on post multiplying A inverse, it become by post multiplying we will get A inverse identity into A inverse, because we are post multiplying here, and it will be P into A inverse. Okay, as we know that A into A inverse is equals to identity. Okay, so this will be A inverse and this will be B into I identity. Okay, because it became identity, so we will have A inverse is equals to B. So by applying the transformations, we will get the inverse of A, that is equals to B. Okay, so if we do the example here, like that I have this matrix A, which is 0, 1, 3, 1, 2, 1, 3, 3, 1. Okay. Now, if we apply the linear, the transformation here, used by the use of elementary transformation for inverse, we will write it into A is equals to IA. Okay. And by performing the transformations, I have done this example too in the inverse topic. So by performing the transfer, we will get our inverse B, which is equals to, we will have to make this A to identity and we have to apply same transformation on this identity, and that will be equals to B into A. Okay, so this will be equals to identity is equals to B into A, and the corresponding B matrices will be is my inverse. A inverse is equals to B. You can do this example, okay, by the use of elementary transformation. Just try it out. Okay. Okay. Now let's just do a particular example of reducing a matrix to its normal form. Reducing a matrix to normal form. So for reducing a matrix to normal form, let's just see that this is the matrix that I have. That is 1, 4, 0, 0, minus 1, 1, 3, 1, 2, 0, 0, 0, minus 3, 2, 4, 2. Okay, so this is the matrix that I have. Now I have to apply the transformations and we have to reduce this matrix to its normal form. Okay, so let's just try to reduce it. So we'll apply in R2 first. R2 minus 4 R1. Okay, and we will get 1 minus 1, 2 minus 3, and this will be 0, 5 minus 8 and 14. Okay, and these will remain same, 0, 3, 0, 4, 0, 1, 0, 2. Okay, now in this matrix we will apply in C2. Okay, we have to make all these uh, by the help of, okay, now we will do that by the help of this element, because it is we have this one here. So by the help of this we'll make these elements as 0. Okay, so we will apply C2 as C2 plus C1. We can apply any transformation like row transformation, we can apply column transformation. So I am just using both of the transformations here. Okay, C2, and we'll apply in C3, C3 minus 2 C1. In C4 we will apply C4 plus 3C1, and we will get the matrix 1 0 0 0, and this will be 1 plus 1 0 5 3 1, and this will be 0 minus 8 0 0, and this will be 0 14 4 2. Okay, now what will we do? So we have this this element 1 here, and this is 5, so we'll just interchange these rows. That is uh, R4 2 R 2. Okay, so after changing these rows we will get 1 0 0 0. This is 0 1 0 2 0 3 0 4, and this is what uh, this is 0 5 0 5 minus 8 14. Okay, so by interchanging the rows we will get this. Now by the help of this element we will make these two elements 0. Okay, so because we have to reduce it to the uh, a normal form, I'll just apply the transformation. So we'll apply in R3, that is R3 minus 3 R2, and in R4 we will apply R4 minus 5 R2, and then we got our matrix as um, 1 0 0 0 0 1 0 2, and this will be 0 0 0, this will be minus 2, and 0 0, and 5 is minus 8, this will be minus 8, and this is 4. Okay, now let's just apply the transformation here, which is we'll apply c4 minus 2 c2. Okay, so after applying this we will make this term 0, so that will be, in applying this we will get c in, we are applying in c4 minus c this. So first will remain same, second will remain same, 0 1 0 0, and this will be 0 0 0 minus 8, and this will be 0 0, this will be 0, this will get 0, minus 2 4. Okay, now let's just reduce it more. So, okay, so we'll exchange these rows, because in the in the normal form we have IR000. So this is the identity matrix of order R. This is the identity matrix also. For this we have to make this element something. Okay, so let's just interchange these rows. Okay, that is we are applying R3 to R4. So after applying the transformation R3 to R4, this will be minus 8, and this will be 4, and this is 0, and this is minus 2. You can write this in a separate matrix. I am just changing the transformation here. Okay, now after this we have to make this element 1. So for this we will apply in c3 into minus 1 by 8. Okay, so after this we will get the matrix as 1 0 0 0 0 1 0 0, and this is 0 0. We are applying minus 1 by 8 na. Okay, so this will be 0 0 1 0, and this is 0 0 4 minus 2. Okay, this is what I got. Now I have to make this element 0, okay, and this element 1, because it is, first we have to focus on the making identity of order R. Okay, okay, so let's just make this 1. So for this we will apply in c4 minus 4 3 3, and by applying this will get 0. Okay, write this in a separate matrix too. Okay, and for making this 0 we will apply um, in c4 into minus 1 by 2. So after multiplying this element into minus 1 by 2, we will get this as 1. So we get an identity matrix of order 4. So we are getting here identity matrix of order 4 here, because this is the non-singular matrix. Non-singular matrix. Okay, so this is I4 here. We have got this into the normal form like this. So if this is the case, because this is the non-singular matrix. If we have a case where we have a singular matrix, okay, let's say this is the we have this singular matrix which is of 3 cross 3. Okay, and the rank of this matrix is 2. Rank of this A is 2. Then the corresponding normal form here is I2 I2 0 0 0. Okay, and what is this I represented here? I is basically 1 0 0 1 and 0 0 0 0 0. This is the identity matrix of order 2. This is I2, and all the other elements are 0 here. Okay, so this is the normal form. This is how we can reduce a matrix to its normal form. And these normal form, canonical form, echelon form, these helps us in finding the basis in reducing a matrices. And basically they perform the task is to simplify the calculations, to simplify the equations that we have to do in the linear equations, in so many forms, quadratic equations, in characteristic equation. We have to perform it in many ways. Okay, so this is all about the reduced forms of the matrices. These are the forms that in the by these forms we can reduce any matrices into these forms for simplification. Okay, thank you.